I hope everyone is in good shape. So we are now entering the second week of the school, and we are delighted to have Dr. Dian Puspita Triani to give lectures today on galaxy evolution and what is dust, stellar interstellar matter. I mean, okay. Now I would like to briefly introduce Dr. Triani. She got her bachelor's and master's degree in astronomy from ITB, and then the doctoral degree she got from Swinburne University in Australia. And she is now the postdoc fellow at ANU, Australian National University. And her research of interest is in
Sorry, Bu Hesti, I lose you. I can't hear. Yeah.
Okay.
Now it's good.
Can you hear me now? Okay, yeah. I've just introducing you that you are now a PhD fellow at the Australian National University, and your field of interest is in the I think we have a problem with the Hello.
Yeah.
Okay, sorry, we have a technical problem here. No, I think we just start with your lecture today. Okay.
Great. Let me start sharing my screen. Thank you, Bu Hesti, for introducing me. Again, my name is Dian Puspita Triani, but I was usually called Pipit. So let's start with Pipit. So you can call me Pipit. If you're Indonesian, you can say Kak Pipit. I am now again a postdoctoral fellow at the Australian National University, and today I will deliver a lecture on the theory of galaxy formation and evolution. Sorry, for the admin in the seminar room, can you switch the camera to show the participant instead of the... Yes, that's better. Cool, thank you so much. Yeah, so today, yes, I will give a brief introduction for how we think the galaxy forms and evolves theoretically, and how we compare with the observations. This is like all of the lectures that I will explain today in a picture. I remember that Bu Hesti taught me this in a cosmology, in an introduction of cosmology. So in the theory of Big Bang, we believe now that it all started with one big clap, Big Bang in the beginning of time. And then there's a tiny seed of density fluctuation in the early universe that is then got inflated. So then we have the dark ages where the baryons and the photons is still coupled. So the universe is all of the hot plasma soup, and the photons that gives us lights is basically just like still scattered with the free electrons. And then that is called the dark ages, and it's not observable until now. The universe slowly expanding, and then the first stars about 400 million years after Big Bang. That is due to the density fluctuation does grow, that I will touch later. And then the development of galaxies and stars and planets grows from that point until now in the universe history. And now we know that the expansion of the universe is accelerated, blah, blah, blah. So like this is like all of the theory of galaxy formation, the evolution of universe in one picture, basically. Right. And the outline of my presentation today. So I will touch base on introducing you to the universe that I understand now. And then we will talk about the structure formation, the galaxy formation, and how to model them both in the first talk. In the second talk, I will focus on the chemical enrichment and the dust enrichment of the galaxies. And then we have a hands-on when we will try on the model. So there's semi-analytic model of galaxy evolution later. But we can, like, if my lecture ends a bit sooner, then we can have more time. And I have prepared a tutorial and a hands-on for the hands-on that we can download later. I'll have all of the information in the slides after this one. So let's talk about the universe first. Okay, and if you have question in the middle of the talk, please type that on the chat box, and we will have the session that I can read the question later, just like in different time during the talks, or you can also raise your hand and unmute yourself at the question sessions. So yeah, let's talk about the universe first. We now have a theory of the lambda cold dark matter universe. So Fritz Zwicky in 1933, so this gentleman here, he used a virial theorem to compute the dynamical mass of coma cluster. So we can observe the velocity dispersion of the galaxies in the coma cluster. Coma cluster is shown in this. It's like a big clusters of galaxies. And from the velocity dispersion, then we knew the kinetic energy, and then we can compute the dynamical mass. And Fritz Zwicky found that the masses from the velocity dispersion is much larger than the mass that we got from looking at the stars in the galaxy. So if we assume that like the coma cluster has 800 of galaxies, and each galaxy is like Milky Way, so the mass is like 10 to the 9 solar mass, then we can compute the luminous mass. But so the masses that cause the galaxies to move, so it has the velocity, is much higher than its luminous mass. So if there is like some hidden mass, so that's how the idea of the existence of dark matter happened. And then there's another, like from that, there's another more support to the existence of dark matter. So for example, Farah Rubin in her work, so Farah Rubin and Ford, 1970, they observed the rotation curves of the spiral galaxies. So the light profile, so like it shows in the first figure here. I hope you can see my cursor. So the rotation curve of the spiral galaxies, the light profile shows that it peaks in the center. So it reflects like the visible mass in the galaxy. So we can see the mass from galaxies in forms of stars. The light profile peak in the center. So this is the distance from the galactic nucleus. This is the center of the galaxies, and this is further away to the outskirts of the galaxies. And we see that the light profile says that the visible mass peaks like near the center, but the velocity, the speed in the galactic plane is more like flat. So it's not peak, it's still flat and extending to the outskirts. So there must be some masses here that is not seen. So it's like some hidden mass. A couple of groups also find the supernovae 1A light curve shows that the universe is expanded at an accelerated rate, which found the idea of the dark energy that can explain this acceleration. So that's like the early work on the dark matter and the dark energy idea. But after that, lots of galaxy surveys. There's like SDSS in optical and 2D FGRS, which further constrain the parameters of the universe and found that like there's also like the discovery of the CMB here that shows the fluctuations. So CMB is the cosmic microwave background, which is it's an accidental discovery from, I forgot its name. Yeah, it's an accidental, like a telescope pointing anywhere in the sky. They found this microwave emission that is persistent, but they don't know what is the source of this emission. And then another group of theoreticians want to find this. So the observation and the theoretician groups are two different groups. So the observers don't know what is the source of this microwave energy, and the theoretician wants to find this energy, but they have not made the observation. So then they talk to each other and conclude that so this microwave energy, this microwave emission comes from, remember, there's like a time where the photons decoupled from the electrons, and this photon is basically anywhere in the universe. But now, because the universe is expanded, the photons has been also stretched to a very long background, which is now discovered as a microwave. So before now, this photon can be like in optical, and like after now, it can like stretch more and might become like radio or like even or like longer wavelength like that. So yeah, that is the how the lambda CDM universe founded, and I think like this shows like the current constituent of the lambda CDM universe. So our universe is built 73% by dark energy, which caused the acceleration in the universe, and 23% of dark matter, and only a very small component, so like 4% of baryon. So baryon is the thing that made us, right? Like carbon, hydrogen, gas, dust, stars, everything is in baryons, including us humans. And in this baryon component, the other non-luminous components makes up most of it. So intergalactic gas, neutrinos, supermassive black holes, it makes up more than around 3.6%. And the luminous matters that we can see, like the stars and luminous gas, is only 0.4%, which also shows how inefficient star and galaxy formation is, which we will talk about later. Right, so that's an introduction of the universe. I'll take questions if you have for the first part of the lectures. You can type the question in the chat box or raise your hand. Okay, should I just... Hiskia has his hands up.
Yeah, all right. So my name is Iski. I want to ask a question. So if I'm not mistaken, you just said about the cosmic microwave background. So based on my understanding or my knowledge that the universe in the past has a wavelength, which was higher than the present or right now. So at the past, it means that all of the sky is bright. It was not dark, wasn't it? Was it right?
Okay, it's a very good question. So is the sky always been dark like now? So it depends on what we define as dark and light, right? Because even now, I think our sense of dark and light comes from the optical, because we have eyes. And then when we have, so we see dark as the lack of optical light. So in the past, the cosmic microwave background might be the cosmic optical background. Is that what you're saying? So then we can detect the CMB with our own two eyes, and then the universe will look like very bright. I think that's the essence of your question, right? But then again, the universe has like a very long extended history. It's 13.8 billion years, while the human history is like very narrow in terms of the timeline. So it might be that like in the past, we can detect the CMB with our own two eyes, but we are not existed yet at that time, I think. Does that answer your?
You actually answered the question, but the conclusion is that the universe in the past was actually bright when it comes to the visible light or cosmic optical background. All right.
Yeah.
So thank you so much.
Yeah, or if we have a superhuman eyes that can look at microwave, we might see it as even really bright right now. So another perspective. Okay. Another question. Is there any question in the chat? Right. No. Okay. Let's go to extragalaxies. Here shows lots of types of galaxies that have been observed in the universe. So I'm sure you have seen this diagram. There are elliptical galaxies, there are spiral galaxies, and even the spirals have lots of morphology. They have intermediate spirals, they have barred, and there's another type of galaxies which is irregular. We can, I'll give you this link later that shows the, you can like point at these galaxies and see their properties. So you can see like how the properties of all of the galaxies with different class vary. Let's take the basic of the galaxy morphology first. So in general, there are two part of the galaxies. We know there's a bulge or the elliptical components, and there's disk or the spirals components. So these two components have physical differences. It has different gas content. The bulge is usually lacks of gas, while the spiral still has lots of gas going on. And this gas is basically what made stars. The stars formed from the gas in the galaxies. So it shows that in the earlier times, we think that the bulge galaxies with big bulge component or like purely elliptical component has no more gas, and then it made the stars in one go, so in one burst. The different component also differ in the integrated color. So I saw it here, the bulge is usually redder, while the disk is more blue. I hope you have learned before that in the stars, like the star's color shows its physical properties. So the red stars is usually colder and older than the blue stars. So the blue stars is usually young and very hot, very luminous, very massive. And if we see like this bulge is red, then we can think that it will consist of red stars, which is old and colder. And the differences of the bulge and this is also in every star formation rate. So the disks still have current star formation rate is still forming stars from gas, while the bulge, because the stars is old, it has stopped or like very low star formation rate. So yeah, the elliptical galaxies basically have a very big bulge component, the bulge dominated, while the spirals basically are dominated. So maybe have bulge, maybe not, but like it has a massive spiral components. So that's what differ there's lots of types. Basically, it's a different combination of the ratio between bulge and the disk. But is that simple? Well, I said looking at these figures is more like looking at a picture with lots of people with different age and different weight and different physical appearances, right? So we see like a statistic of galaxies in the sky with different properties. It might show the different histories of galaxies. It might show like the different ages of galaxies. So it's like looking at, say, people in one mall and see how different they are. They're like babies, there are older generation, and there are teenagers, like adult. And basically simplifying that, we just divide galaxies into these types to make us understand better like the histories of galaxies. So we see that the spirals are usually gas-rich, dust-rich, still star forming, while the ellipticals has been depleted of gas, the star formation has stopped, and it's usually red and dead. The different morphologies of galaxies that observe form our historical view of galaxy formation. So the classical view formed around 60s and 80s, that's basically said that galaxies evolve individually or in isolation. And the physical properties that we can observe now is dictated by the star formation history. So in the classical view, we think that the elliptical galaxies have starbursts like early in their formation. So it has prompt conversion of gas into stars, while the spirals has more gradual consumption of gas. So the gas form into stars gradually, and it has constant and continuous star formation. But in the modern view, we find that the galaxy formation is founded first by the dark matter formation. So the gravity first governs the hierarchical formation of the dark matter halos. So there's like structure with purely dark matter that forms first, and then the baryon will collapse into the dark matter halos, into the potential of dark matter halos, and then evolve into galaxies that we observe now. And in the hierarchical formation of dark matter halos theory, we know that we think that the low mass halos collapse first, and then there's like mergers. So then the smaller halos will form more massive halos, but then these mergers also govern the morphologies of the galaxies. So the mergers will dictate whether the mergers will grow the bulge, basically. And there's also like the effect of environment in forming the dark matter. Right, so that's the historical view of the galaxy formation, and then we have the observables. So I'm a theoretician, and as a theoretician, what we're trying to do is stitching up the observation and trying to find an explanation on how do the universe evolve so then it can match the thing that we observe from redshift 0 to higher redshift. And we can like stitching all of the pictures together. But the observables, this is like I will show several observables that we use as the constraint of the theory of galaxy formation. So this figure shows the observation of galaxies in different wavelengths. So let's look at here first. So this shows the full-fledged wavelength of the electromagnetic light, from the very long radio wavelength, microwave, infrared, to the very energetic gamma ray. And before we talk about how we human have the sense of observing from our own eye. So our own eye is here. We can only detect the light in this very narrow waveband. So that's why, like earlier, we can only see like the optical observations of galaxies, which is dominated by the stars in the solar mass. So it's optical lights comes from these stars. But once we have instruments that can help us to extend our observation to even like longer wavelengths, so then we can now observe ultraviolet, X-ray, infrared, and even radio. We have telescope for that. Then we can start to observe other components of the galaxies and the universe. So this is an example of the whirlpool galaxy, so one galaxy. In radio, at 60,000 nanometer wavelength, it shows a very cold component of the galaxies with the temperature only 600 Kelvin. It shows the distribution of the cold gas in galaxies. While in infrared, we see there are two components that dominate the infrared lights of galaxies. There are cool stars, so stars colder than red, so that's why it's called infrared. And these stars milk the bulk of mass in the galaxies, but only contribute very little in the total light, total emission of galaxies. But not only stars, the infrared also dominates by dust. So dust is a cold component as well in the galaxies. It absorbs light from the hot stars. And then after it absorbs light, it will become hotter. And when it reach a temperature, like a critical temperature, it will start emit the infrared lights. Then optical, like what we see is the stars. It's like basically around the size of sun. And ultraviolet is very hot, young blue stars. Then we can also have observations as X-ray for the whirlpool galaxies, which observe the hottest region where it's a very hot gas where the atoms are ionized. So then we now not only see stars and galaxies, but we also see the dust and gas, like very cold gas, very hot gas, that we try to explain like all of these components later with the model. Another observables that is very important for the theory of galaxy formation and evolution is the star formation rate density. So what this diagram shows you in the y-axis is the rate of the galaxies in forming stars. So the unit is solar mass per year per unit volume. So it shows in 1 unit volume in the universe how many stars are born per year, basically. And this is the look back time. So this is 2 gigayears ago. This is 12 gigayears ago. And this is like the redshift that associated with the look back time. And we observe that the star formation rate, like the total star formation rate density in the universe, is actually peak at around redshift 2. So the universe forms stars. So this is like, let's talk about like from the very early universe. It forms stars and it's forming stars even more rapidly until it reached redshift 2, which we call cosmic noon. And then the degree of star formation rate then decreased until now. So we are not actually forming stars as much as we used to be like 10 gigayears ago. And we're thinking of like how, like, so this is what we observe and we're trying to understand like how this is happening. Another thing that we can observe as well is the luminosity functions. So luminosity functions, basically what I show you here is the histogram. So in a histogram that shows the, like the bar histogram, this is the same thing, but they just don't put the bar here. This is basically the histogram. which shows the distribution of lights in galaxies, like in the universe. So this is showing the number density per, so it's like per unit volume again. And it shows the fainter galaxies, where this shows the brighter galaxies. So what we know from here is the fainter galaxies is much more than the brighter galaxies, so the brighter galaxies has a lower density. And we can observe this luminosity function in different filters, in different wavelength, and in different redshift. So then we know the evolution of the number distribution of galaxies. The luminosity function is usually described by a Schechter function, which looks like this. So the L star and the alpha and the phi stars is the variable of this function. And it's basically what looks like this. And yeah, so this is like the observables that we try to constrain in the model. And I'll have the mini quiz after this, but I'm having a flow for questions. I'll wait for a couple of seconds. If you have questions, you can just raise your hand. I can see you in seminar room, so you can physically raise your hand if you're in seminar room, or type your question in the chat box. No? 10, 9, 5. Okay, right. I have a mini quiz here, but I think I'll give 10 to 15 minutes for us to do this quiz. So we talk, the number one, we talk about the coma clusters, Fritzwick's work, but I want us to compute by how much the dynamical mass of the coma clusters is higher than the luminous mass. Okay, let's give it until, let's have 10 minutes of silence to do this. And if you have a question in this 10 minutes, you can just raise your hand physically. If you're in seminar room, raise your hand in Zoom or type into a chat box. Sorry. There is a question in the chat box. I will read this in 10 minutes. So you have 10 minutes to think about questions. And this is 11:45 here. So at 8:45, I will read through the questions and try to answer them. So if you want to think about the question, do it now, type it on the chat box. Or if you want to ask it later in person, like by raising your hand, it's okay too. So thank you, Aulia, for sending that question. Right. For number 1, I think we missed the radius. So I haven't give you the radius of the common cluster, which is 10 to the 6 light year. So let me put it here. Yeah. Can I tell you? Right, I cannot. I'll put it in the chat box. Okay, we have 2 minutes left though. So I'll give it for the hands-on session later, but I want you to focus on number 2. For these last 2 minutes. Okay, thank you for doing this mini quiz. So there's what is the order? Okay, how many people have finished number 1? Can you raise your hand? Right, Shubham has finished. So yeah, an order of 3 or more. In number 1, we use basically the Ferriel theorem, shows that 2 times the kinetic energy should equal to the potential energy, and the potential energy here is the gravitational energy, so gmm per r square, and the kinetic energy is the half mass velocity square. And then you can just like, yeah, there's lots of calculation, especially with all of the units, but it's very big. It's about 1,000. Yeah, correct. So number 2, my eyes is on the participant in the seminar room. So you can raise your hand if you think the spiral, so for number 2, there's A, B, C, D, E, F. And if it's higher, a spiral, if you think what I say is correct, then you raise your hand, okay? So compare to typical spiral and elliptical galaxies based on their color. So do you think it's correct that the spirals are red? How many people think spirals are red? And elliptical consistently are blue. Right, so other people know. Okay, yeah, but this is false. The spirals are usually bluer than elliptical. Now, star formation rate. Spiral has higher star formation rate than elliptical. Is it correct or not? Very good. People in the seminar room. Good. All right. So yeah, that is true. That is correct. So spiral has typically higher star formation rate than the ellipticals. Okay, let me pin a minute. The gas content. So is it correct that spiral has lower gas content than the elliptical? So lower mass of gas. Oh, very good. 5 seconds of answer. 5, 4, 3, 2, 1. Good. It's false. So it's higher gas content. And is this spiral galaxy is more metal rich than the ellipticals. So the metal and dust content in spiral is more massive than the elliptical galaxies. If you think this is correct, raise your hand in 5, 4, 3, 2, 1. Okay, so yeah, good. Yeah, the metal and dust content is in spiral is higher than the elliptical. So that's like the gas content and the metal and the dust is more richer in the spirals. Ellipticals is basically all stars. That's what we think it is. Now the bulge to total stellar mass ratio in spiral is lower than ellipticals. Is that correct? Very good. And it's true. So the bulge is smaller. Good job. The last one. So I think we haven't touched this before, but if you use your senses, if you guess, is spiral more massive than elliptical? So the total stellar mass of a spiral is bigger than the ellipticals. Yeah. Okay, 5 seconds. Good. This spiral are usually a lower in spiral mass in the total stellar mass. So elliptical is basically, it's usually typically a very massive red and dark galaxies. So at least that's the one takeaway that I want you to have in this lectures. Okay, let's continue to the complicated process. Okay, sorry, I forgot the question. I have a question before in the chat box. Let me see. Do supermassive black holes affect galaxy morphology and evolution? Very good questions from Aulia. The answer is yes. So we will learn in this section, in the process of galaxy formation, that there is a process called feedback, which is basically lowers the efficiency of star formation. And one of the source of the feedback is supermassive black hole. So a supermassive black hole can have activity, lots of accretion, lots of gas accretion surrounding it. And this gas accretion could be a source of a very energetic event, which can expel the gas from galaxies out to the environment, to the intergalactic gas. And because the gas is expelled out from the galaxies, then it lowers the rate of star formation because now the galaxy has less gas than before, and that process is called feedback. I will explain it a bit later here, but if anyone have more questions, I'll have 5 minutes. 5 seconds, sorry, 5 seconds, 5, 4, 3, 2, 1. All right. Okay, let's go to the process of galaxy formation. What we got from the observation is that in the early universe, we have a very tiny, minuscule fluctuations of the temperature or density in the universe, which is shown by the CMB that we talked about before. But right now, what we observe is the skies is full of galaxies and clusters and lots of structures in the universe. So we have cosmic filaments here, which is in the brighter part is the filaments of masses and galaxies. So it shows the galaxy clusters and basically the concentrations of mass in galaxies. And there's like lots of voids. So the darker region here doesn't have anything on it. So it doesn't have like any masses. So basically right now we see like big structures in the universe, which comes from this tiny fluctuation of temperature or density. The question is how? This figure here shows the density contrast, so in y-axis. So it means like if it's low, then the universe is very uniform. And how is the density contrast evolve with time? So in the very early universe, the density contrast is very low. The universe is very uniform with a but like there are regions that has a little bit higher density than its neighbors. But with time, this density contrast, first, it will evolve linearly. So the density contrast will increase with time until it's reached a critical density where now the overdense region can collapse under its own weight and forms a structure. So it collapses under its own weight, and because it has now more density than its neighbor, it starts attracting more mass. So the density contrast increase again, and then it's again collapsed under its own weight. So this is like the oscillating things here, showing a very violent relaxations where the structures from dark matter forms, and until it reaches a virial equilibrium, then now we have like a bounded structures of dark matter that we call halos, and then it will again the density contrast will again increase. But now, so the blue line here is the dark matter. But now, because the universe has these structures of dark matter, that is bounded by gravity, the baryons, which is before coupled with photons, and now the baryons and the photons has been decoupled. The baryons now, because it has mass, it falls into the dark matter potential well, and this is what will form the galaxy. So the baryons is in form of gas, and that gas will later form stars, and the stars then will make metals in its own core. So the stars transform hydrogen to more massive elements. So elements with like oxygen, carbon, nitrogen. And then when the stars when the stars die, it will eject these elements to the interstellar medium and pollute that. And that's how we get like lots of elements in the universe. And then that elements can condense into dust. Yeah, so this is showing how the dark matter density contrast evolve in the universe. So how do we model that? There are two efforts in doing this. The classical, the first effort in modeling this is using what called Kresshefter formalism. So this is an analytical statistic models, but now the n-body simulations take over and it's more common to use. So in n-body simulation, what we do is we make a box with a very big box size length, and we fill them with particles. And we assume that these particles only is dark matter, so it only has mass, and it can only it can only interact gravitationally. So this shows this box shows what we model at redshift 6, and then we evolve that we implied gravity in this particle, and then this particle will evolve and make overdensity regions. And there's also like a region with lower density, and the yellow dot here is the region where the overdensity have reached a critical value and then has bounded to form a structure. So this is showing what the structures look like at redshift 2, and then we evolve them again, and this shows what the structures look like at redshift 0. So this figure is from Millennium Simulation from Paul Springle. And what do we do next is we connect the dark matter halo over time. So see here, we evolve the particles over time, and then we define which are the structures, which now we define as the yellow dots here. Now we have yellow dots at redshift 0, we have yellow dot at redshift 2. What we do is we see like the particles constructing the yellow dot at redshift 0, and connecting it with the halos or the structures at redshift 2. So this is showing, for example, a formation of this big structure. For example, this is redshift 0, right? And we define the halo and subhalo at each boxes as bounded or virialized overdensities. So basically, if one region have overdensities 200 times of the average density, then it is a subhalo. Then we identify the progenitor and descendant of the halo based on the particle member of each halos in simulation with different time. So for example, if this halo at redshift 0 and this is the halos at redshift 0.5, if they consist of the same particles, then we think that this halos comes from these halos and these halos earlier in time. And then we connect it again with the box at higher redshift. So for example, redshift 1. So if this particle, if the particle in the halos here consists of the same particle that construct these halos, then we think that this is the progenitor of these halos, and this halos is the descendant of these halos. Then after we define the halo, we identify the progenitor and the descendant, so then we can construct, this is called merger trees of the halo. Then we compute the properties of each halo here, so the radius, the virial mass, and the virial velocity of each halo. Now that is how we model the dark matter halos in the universe. And then the dark matter halos are the host for galaxy formation, and baryon will evolve within these structures. And there's like lots of complicated processes, including the baryon, because the baryon is not only has mass, it also has it has pressure, for example, and like it can emit things, not like dark matter that can only interact gravitationally. Baryon can interact also hydrodynamically. So that's why the modeling of the baryon is much more complicated than the dark matter, because it has temperatures. So there's like cooling processes. It can transform into stars. It can transform into minerals and dust. And we have feedback mechanism and other mergers. So to model galaxies, there are usually two approaches. The first is using the hydrodynamical simulation. So hydrodynamical simulation is similar to the N-body, but now with not only implementing gravitational force to that particle, but we also includes all of the hydrodynamical processes above, which takes a lot of computer sources and time. So this can take months to run, but the process is really detailed. We can know what happens in each particle, and we can know like the resolved properties of galaxies. But yeah, it's not flexible. It can take months to run. So if we want to, like, if the physics is not well known, then we need to like test it, and hydrodynamical is not a good option for that. Instead, we can use a semi-analytic model, which builds galaxies as a post-process on top of the halo merger trees. So we know that there's like big N-body simulation that has been run, which has the dark matter halos, and then we can, as a post-process, we can evolve the baryon in each of the halo. The process it's very fast to run. You can run it in like 5 minutes. I'll show you how in hands-on session. So it's flexible in trying formulas and testing new physics. It is very fast to run. It can run in your own computer, but it only provides integrated properties of one galaxy. So we cannot see each particle in the galaxies. So because we take one halo from the N-body simulation and we evolve the galaxies in the whole halo. So what people usually do is to match the observed like statistic of galaxies, like the luminosity function. They first use the semi-analytic model to try lots of different formulas. And if that's good and we want to see the detailed process, then we use that formula in the hydrodynamical simulation to see the more resolved processes. And in this work, we'll use a semi-analytic model. And this is the processes that are in the semi-analytic model. First is the gas infall. So in the gas infall, we have the halo, right? And the halo is very hot because it reaches virial temperature. Now the pristine gas in the universe, which is the baryon, is falling into the potential well of the halo with this formula. So the mass, the infalling mass, have to reserve the universal baryon fraction in the universe, which is usually 2%. So mvir is the halo virial mass, and the mb is the total baryon mass from the previous snapshot. So we want to keep the baryon fraction in the universe at a universal value. So for example, the 2% of the virial mass is, if it's bigger than the baryon mass from previous snapshot and from previous redshift, then we infall more mass into that halo. But if it's bigger, then we don't infall that, but we kick the mass out from the galaxies. Now, because the infalling gas mass, the infalling gas temperature is very hot, it will later cool down and forming the interstellar medium. There are lots of cooling channels. So the gas is like really hot. At the early universe, it can collide with the CMB photons and lose the energy. This process is called inverse Compton scattering. But in the lower redshift, there are like more cooling channels. So the bremsstrahlung is for very massive system that have lots of ions, and the ions can accelerate the electron and have bremsstrahlung emission, so the gas can cool via that emission. Metals are middle line emission here is a very effective process. So metals is a very effective coolant for gas because it has higher atomic number. So basically, if the gas ionize these metals, it will, the cooling process is very efficient. There's also cooling process involving molecular hydrogen. We do that in the model, and then we have cold gas. The cold gas can be differentiated into molecular or atomic hydrogen. And the molecular clouds are much more dense than the atomic hydrogen. In this molecular clouds is where the stars form. So we have star formation inside the molecular clouds. Usually, there are lots of models that use this what called Kennecott-Smith relation. So we have the so this is the efficiency, star formation rate efficiency. Basically, if the mass of the cold gas is above some criteria, it will form into stars with the efficiency of alpha SF across the dynamical time scale of the disk. And these stars is like formed in the disk, right? So the stars are like in the model, the stars are formed in the disk first. And how do the bulge have stars? I'll explain that later. The Koenig-Smith relation have lots of updates. It's a very old relation, so it has lots of updates that now, that before it's only known that the stars form from cold gas, but now we know that stars form from H2, from the molecular hydrogen. So the ratio of the molecular and atomic hydrogen depends on the pressure in the ISM, and the pressure can be computed from the gas density distribution, like the gas distribution. Yeah, so we have all of this formula and we implement that in a model to form stars. So now we move a fraction of mass from the cold gas to stars. But only having star formation, it's too efficient for the observable universe. So we have talked about the luminosity function before, right? So this is basically the abundance or the density, number density of galaxies with this total luminosity. So for example, this is like the abundance of galaxies with 10 to the 8 luminosity, like solar luminosity in filter, like in B filter, SDSS filter. So if we only have the star formation rate, then we have this blue line from the model, while what we observe is the red dot here. So we have less. So this is low mass or faint galaxies, and this is high mass or bright galaxies. So we observe less low mass and high mass galaxies than what we model, than what is like the star formation in the model. So then we need mechanism that slows down the star formation rate only for these very low and very massive galaxies or halo. We do it okay in the middle part. So I like the process is correct in a fraction of galaxies, but in very low mass or very high mass galaxies, we need to introduce another mechanism so then the model can match with the observation. And this is this process is called feedback. The first source of feedback are stars, so which is called stellar feedback. So how do we model that? There's like lots of process regarding stars or stellar evolution. So for example, lower mass stars can have stellar winds, and the energy from the winds can expel the gas in the ISM out to the halo or even out of the system. What we call in the model is ejected reservoir. And higher mass stars or binary stars can end up as supernovae, which even have higher energy. So we can compute the supernova energy, and then we can compute the supernova energy, and if that energy and how much mass can that energy expel into the halo and to the ejected reservoir. So then if the gas is ejected from the ISM, then we don't have materials for forming stars. Then the star formation will slow down, and it can, this can help the lower mass galaxies, because in higher mass galaxies, because the masses is really large, the potential well is really deep, the supernovae or the stellar winds is not enough to expel the gas. So then we need, so this is the energy released by the stellar feedback, for example. So stellar winds is lower than supernovae. But yeah, basically the supernovae, the stellar feedback can help ejecting mass of the very low mass galaxies, because the potential well is not too deep. So the supernova energy or the stellar wind can help ejecting the gas. But for a more massive, it's good that for a more massive galaxies, this process is not efficient, because then the potential well is too deep for the supernovae to expel the gas. So that's why it doesn't affect the more massive galaxies. But then we need another mechanism that only acts for massive galaxies, and it can expel the gas from a very massive galaxies. And that is the AGN feedback. So this is where Aulia's question comes to play. So in very massive galaxies, they have very massive supermassive black holes in the center, which can host what we call an AGN. So AGN is an active galactic nuclei. So these supermassive black holes can accrete gas with a very energetic events. This can only affect very massive galaxies because lower mass galaxies won't have a very strong supermassive black hole in its center, but very massive galaxies will have this. And there are two modes of the AGN feedback. First, the accretion onto black hole can heat the cold gas, and if the cold gas is like reach very hot virial temperature, then it can go back to the hot halo. So the ISM is basically cold. In the quasar mode, the rapid black hole growth can cause quasar winds that blows out gas to its surrounding. So again, it's like the supernovae and the stellar wind. The IGN also have the radio mode, which is the heat, and the quasar mode, which is the wind that can later expel the gas to the halo and eject the reservoir. So that's how we make the luminosity function or the stellar mass function agrees with observation. But now, we can only explain the disk galaxies, right? Because before I told you that the star formation, like what we are talking about here, happens in a disk. So how do bulge get its stars? We in a model, the bulge form its stars in so the thing that govern the galaxy morphologies is the mergers. So in major merger happen when the mass ratio. So in a merger, we have a central galaxy and a satellite galaxies. So the central galaxies is more massive than the satellite. So this is, for example, a merger of two galaxies. If the mass ratio between the central and the satellite bigger than some threshold, then it is called major merger. In a major merger, both of the central and satellites are disrupted because it's too violent. So it will make a new system, and the stars from both systems are placed in a bulge, in the spheroid part. But if the mass ratio between central and satellite is not that big, it's below the threshold, then the bulge will not be disrupted. The central will not be disrupted. Rather, the satellite stars are placed in the bulge of the central, and the central star will central stars is untouched. So the disk stars in the central will still be in the disk, while the bulge is still in the bulge. When a merger happens, there's lots of cold gas, right? Because it's two systems merging, then the cold gas in both systems is also merging. So it can trigger starburst. So starburst is when this cold gas transforms into stars. And the stars that is newly formed in this merger is placed in the spheroid part, so in the bulge. So that's how the bulge is formed in the model. Right. Okay. So this is the summary of the first part. We use a meowth model to test lots of formulas to describe the physical processes of galaxy formation on top of the halo merger trees. So the prerequisite of this model is we have to have the n-body results first. We have to have the dark matter halo merger trees first, and then we evolve the baryons using the gas infall, cooling, star formations, lots of prescription, lots of formulas that reflect the physical properties that I talked about before. And yeah, so I'll have another mini quiz after this, but we have time for questions. So if you have questions, I have one question in the chat box, but if you have more questions, you can raise your hand. Oh, sorry. Okay, let's see the question from the chat. Is the energy emitted by supernovae to the hot halo a prominent part of what would from hot bubbles in star formation? What do you mean by hot bubbles here? Is it the bubbles where the star formation is low because the temperature of the gas in the bubble is hot? Is that what you mean by the hot bubble? Okay, yeah. Right. So yeah, the energy by the supernovae is also one of the mechanism for the feedback is also the hot bubbles. So the supernovae will heat the surrounding gas, and this gas, because it's hot, it cannot form stars, and that is what we call the hot bubbles. Is there any other questions? If not, let's play a little bit quiz again. So I have lots of halos here, and this is the time. Halos in the horizontal line forms at the same time. Oh, we will have another questions after this quiz. So if you, I'll have 10 minutes. Yeah, so 12:30. Yeah, so we'll have about 5 minutes in the quiz and 5 minutes question times after that. So if you want to think about questions, you can type your question in the chat box now, or you can raise your hand. Right, so the quiz is like this. So I have lots of halos here marked by the number. So we will play the progenitor and descendant quiz. So for example, number 1, what are the descendants of the halo G? We'll have 10 minutes to answer. So yeah, this is like number 1 is the game of progenitor and descendant, and I have like different color here, which shows the main progenitor line of halo J, other halo. And number 2 is based on data on this table, decide whether a galaxy populating halo J will need gas infall or whether it will need feedback, and by how much. Remember that when forming galaxies, we want to keep a universal baryon fraction. So for example, 2%. So 2% of the virial mass should be kept at all time. If we have less mass, then we will have an infall. If we have more mass, then we can have a feedback. So we'll have 10 minutes. And you can also type your question in these 10 minutes. I think you can do this less than 10 minutes. So if you have done, then maybe raise your hand. So we can have less time. Okay. We have 3 minutes left for this session. So yeah, I think people have finished answering. So yeah, his answers. The descendant of halo J is I and J. So there are 2 descendants, and the progenitors of halo H are A, B, E. And the main progenitor line of halo J is the blue. And it needs gas because it has less mass. Really? I haven't really. But yeah, we can talk about it in the hands-on session. But there is a question from Ashraf. We know that the universe expanded at a certain rate. Does the expansion affect the structure of the astronomical objects within the universe itself? The answer is no, because under gravities, the bounded structure is kept by the gravity. So the expansion of the universe affect the distance between galaxies, but not the structures inside galaxies, because it has gravity to keep its structure. I hope that answers. And yeah, I think that's enough for me. I'll give it back to Bu Hesti.
Hi. Hello. Okay. So we have break now for 15 minutes, and we gather again at 10:15, I think. Okay.